Hello, everybody, and welcome to the third day of the 16th OpenFOAM Workshop. This session is Heat and Mass Transfer 3. So we've got 4 speakers in this session, each with 15 minutes. Our first speaker, who I'd like to introduce, is Mr. Mohammed Asad Yaman. So Mohammed, if you'd like to turn on your camera and you can you can unmute yourself and please share your screen. And feel free to start whenever you're ready. Everybody, please, as always, let's get a good discussion going. So ask your questions in the live Q&A, or you can put some chat in the discussion forum as well. Thanks very much.
Thank you for your introduction. Can you see my screen now?
Yeah, I can see your screen and I can hear you, so you're good to go.
Okay. So I'll just start. So my name is Mohammed Asad Yamin, and I am in the second year of my PhD, in the beginning of second year at the chair of modeling and simulation in University of Rostock. So today I will present my finding about the 3D thermal analysis of the footwear with the open source software OpenFOAM. So, okay. So can you see my next slide? It's going.
Yeah.
Okay, so in the content, I will start from motivation, then the mathematical modeling, then implementation and validation, results and discussion, summary and conclusion, and then you can answer questions. For discussion. So from the beginning, from the motivation, I want to introduce the modeling of the human outwears like footwears, clothes, helmets, and the gloves are very important and taking very importance day by day, because they due to some crucial weather conditions, working conditions like in the fireworks and in the forging and casting and like the sport activities, and also in the championship like in the sports. Just for the motivation, this video quality is a little bit of that, but you can see, yeah, it's running. Its feet start burning, like you can see it start burning its feet. So actually the modeling of the shoe is taking very interest, because what happened in this situation, the temperature increase, the moisture inside the shoe become more heated, and due to this reason, due to the friction between the socks and the shoes, become more and more. So for the porous material, we have in this situation, we have the fibers, water inside the fibers, and the water inside the fiber, the liquid water, and the water going from fiber to the liquid water, and this you can see that we have the 3 types of the water: vapor, bounded water, and the free water. And this the transition between these, we have absorption, desorption, conduction, and evaporation between also. So, but in this model, the sweating is not considered in the beginning. So if the broader view of this, we change this material, because this material has some physical property: density, thermal conductivity, and heat capacity for the liquid water, bounded water for the dry fibers, and the air and the vapor present in the moisture. So I, with the more than 26 empirical formulas, equate them, and then at the end we have the different new material with the relative humidity and with the relative physical properties. So at the for the big mathematical model, we have the 4 equations for the transport of equation: water vapors, bounded water, and the liquid water, and some parameters which I showed before. You can see for the bounded water, this equations for the liquid water, and for the water going from gas to liquid to gas, and then solid to liquid, liquid to solid, and this gas to solid, this thing. So after this, I want to explain a little bit about the implementation and validation. The implementation I implemented for the, we implemented 1D model code in the Python and the 3D code in the OpenFOAM solver, volume 1712, and the solver name is CH multi-region foam. And this is actually the extension of this solver. So we add just 2 regions for the fiber and the foam and some field variables, some boundary conditions. And actually, here in this study, I consider this the fibers, because the fiber region and not the food region, because in the reality, you can see actually the heat content and the moisture is coming from the shoe to the sock surface. But in reality, in the future, we will also consider this food region. But for validation, I have used the most important Gibson model, which is used for the validation of the results of this model. So in the rows, you can distinguish for the temperature plots and the vapor density plots, and the columns for the hydroscopic and non-hydroscopic material. For the simulation of the Gibson, I see for the continuous line or the dotted line, and overall simulation is with the dotted data. So it's exactly matching in the hydroscopic material that we will achieve at very little high value, and for the non-hydroscopic, it's achieved very early. So other thing is
hi Mohammed, sorry to interrupt. Would you mind turning off your video?
Gibson from the 19 and 12. So from the after more
Mohammed, would you mind turning your video off? Just because the connection is a little bit weak. So can you turn your video off? Is that okay? I think I can do it as well.
Okay, thank you. So for this one, this already we have submitted this paper last year and last month, and it has accepted, and so it's this model is which I am working for the 1D. So for the implementation for making the geometry, we use the 3D scanner for making this geometry. And after this, because this geometry is very complex with the very small layers, very small thickness, even less than 1 millimeters. So you can see this the socks which we get from this 3D printer, 3D scanner. We have the holes, and it's very difficult to make with the steppy headers, the machine. It's very common. But for the 2D, we have just take up one line and then extrude it, and then results for implemented for the real shoes. But for the 3D actual result, I make just more replica near to this this shield, the shoes with 3 layers for socks here and shoe, and with the different boundary condition is the directional boundary condition on the for the inside on the socks, and for the outlet we have 3 type of boundary condition with adiabatic on the top and bottom, and heat convection on the side. So the vapor density and means the humidity and the temperature is we take as a boundary condition, directional boundary condition of the inlet. So for this temperature distribution, just I want to just the rows is temperature and relative humidity, and for the ambient temperature 25 degree centigrade and 35 degree centigrade. So here you can see, if you see the in the columns wise, then there is that the temperature is so in the more uniform at the high temperature, so the temperature reach very near to the outside and inside of the shoes. So if I show you for the temperature distribution results, so you can see for the ambient temperature 24 degrees centigrade and 35 degrees centigrade for the shoe material polyester, polyamide, and for the polyamide. And so here I am just changing the remaining inside the socks is cotton and the outside shoe is polyamide. So if you compare, you see in the first that there is not huge difference if we compare the 1D results with the 3D results, because in the 1D just the temperature gradient is just in the normal direction to the footwear, but it's mean that there is not a lot of temperature gradient in the side in the direction of transfer direction. So if in the same way, but if you see on the is the ambient temperature 35 degrees centigrade, there are 2 phenomena. One, evaporation is coming into account, and second thing, that comfortable level of the shoe is also becoming very less. But at the end, if you see, if we compare the result, calculate the difference between these two simulations, then you can see the more comfortable level is at if we have the material of the shoe which is made, which having the more thermal conductivity, means the polymer. Here, the shoe will be more comfortable and at the low temperature, ambient temperature. But if the ambient temperature is high, then this phenomena is, doesn't matter which material you are using, the comfort level for the both shoes will be the same. The temperature distribution will be the same. It's very good finding for this. But for same way with the relative humidity in the same manner, which I told you for the polymer polyester, for the ambient temperature 24 and 35 degrees centigrade. So the relative humidity, if you see, if we compare both the results for the polyester minus polymer, because in the polyester the temperature gradient is more, so that's why the more vapors will be inside the fiber. It will make more vapors. So that's why it's a more sweating inside, the more lubrication in between the socks and the sole of the shoe. That's why due to this friction come into account. And if we go same way for the higher temperature, then you can see this comfort level is very less, is negligible. But you can see the more uncomfortable place inside the shoe is present in the sole of the shoe. But if I use, because a lot of data research is present inside the literature, where they have modeled the shoe with the just conduction and convection without master transport. But then we have to also want to analyze in this behavior that how it will act if I use the moisture content and without moisture content. But at the low temperature, you can see this has very less difference, like less than 1 Kelvin, and at high temperature it's also decreased. But I didn't find any data that if it's this 1 Kelvin will remain in the shoe, means this temperature high for 60 minutes, but it will affect on the comfort level of the woman and this thing, but it's still under debate. So, but I want to see for the 1D model, because if I change the thickness of the shoe layers for the socks and the shoe and the then I want to see that does it affect, means the moisture transport modeling will affect. That's why here you can see at the low temperature, if the temperature is very low, then this you can see with the more thickness of the layers, then we have the effect is growing. But at the low temperature, you can see here this is negative effect. Why this is negative? Because this is evaporation is come into account, because it's here the state of the water is changing, but it didn't raise the temperature. So that's why. But in the other case, without moisture transport model, it's the temperature is raising because there is no moisture there. The moisture transport modeling is not present there. So at the end, the summary and concluding, the majority of the temperature gradient in the normal direction in the footwear, and if the sole is the most uncomfortable part of the shoe, and at the 24 degree higher degree centigrade at the ambient temperature, the sole with the higher the shoe with the high heat conduction value is more comfortable, and 35 ambient temperature, the comfortable level of both the fibers are approximately same. But when the footwear is thin, the moisture transport impact is negligible. But the last one, when the ambient temperature is high and the footwear is thin, then the moisture transport impact might be significant. But it's just for with the one this conclusion. But this is for you for the question. If you have any question, this is from my supervisor, Professor Cardiff, and Professor Vigan. So this is all from my side. Sorry for this interruption little bit in the.
Great, thanks, Mohammed, for that talk. I know there was some internet issues, but I think it worked out okay. So we have a question. I think we've time for maybe one question. Have you thought of applying the concept of thermal comfort to your footwear calculations to have an indicator for the shoe performance?
Yeah, because I told you that this thing, because we didn't have any data, because still we have a lot of assumption, because some research I have found that where the moisture content, because here I have applied that the moisture means the sweating is uniform in the whole field, but I found just one data where they said that but this data is just for the naked feet, where they have just at the bottom is more moisture as compared to the top of the shoes. But I think after when I implement this the foot region, then I think it will be the better with the Fiala model to predict that this the comfort level of the shoe. But still, there is no any phenomena for that at this temperature, this comfort level will be the shoe is okay or this. But only one phenomenon can be the pressure distribution. But this pressure distribution is, I think, when you will wear a very small shoes as compared to your feet, this will be the helpful. Otherwise, the most dominant is the temperature, because temperature creates the sweating, and this sweating give the lubrication for the socks to the shoe. So this cause a very huge, if you see in the video, that's a very huge, is the heat in between the shoe. So otherwise, I didn't find any comfortable for this one. And here, which I told you, this is just on the base of the temperature gradient.
Okay, great. Thanks very much for that, Mohammed. If there's any more questions, then you can answer them in the chat. So thanks again. You can stop sharing your screen, and you can turn off your video as well.
Thank you.
Yeah, thanks very much.
Thank you, everyone.
And our second speaker is Dr. Kaspar Dadis. So Kaspar, feel free to turn on your video and you can share your screen. So if Mohammed, if you want to stop sharing your screen. Let me see if I can stop Mohammed sharing your screen.
Okay.
You're good to go, Kaspar.
Okay, you can hear me and see me, yes?
Yeah, I can hear and see you perfectly.
Okay, so I will start sharing now.
Great. Go for it.
Okay, yes, so thanks for the introduction. I will present you today a couplet calculation which involves fluid flow, heat and mass transport as well as phase change. And let me tell you first a few words about the motivation. Probably you all know that silicon is a material which is used in almost every modern device like smartphones and notebooks, but that's not the whole story. Actually, if you think about the history, how the kilogram was defined, so this is what was actually till 2019, this very old prototype stored in Paris. And what changed recently was that the new prototype of kilogram unit is actually made of silicon, and this was done because silicon is actually one of the most perfect and pure materials which can be produced at all. And that's another important application of silicon. And of course, if we think about future, silicon is also one of the materials which is still researched for quantum computers. So I can say in conclusion, the age of silicon is still not over. Yeah, so the question is how do we get such silicon crystals for all these applications? And this is the topic of my presentation. And actually there are many methods which are used for different applications, and they are different in quality and also costs and so on. And I will try to introduce to you a bit all of them. And the simplest one, which was used for solar cells, is the so-called directional certification. And it's a quite simple method. We have actually a container where we melt the raw material, then we have the liquid, then we cool at the bottom, and the liquid freezes from the bottom to top, and we have a moving phase boundary. So it's quite easy to understand, but of course you have a lot of physics here. You have melt flow, heat flow, you can have some forces driving the melt flow, and so on. And the basic idea is also the same for all the other methods, like the Czochralski method, where we pull the crystal out of the liquid, yes? And also for the granulate crucible method, where we have not a container here, but actually a layer of solid silicon granulate, which contains the liquid. And the most complex method is a floating zone method. And in this method, you have actually the melt, which is actually sitting on the crystal itself. So the melt does not have any contact with other materials. So it's actually was the method which was used to produce this kilogram unit material. Yeah, so as I said, the basic idea is quite simple. So we have to freeze a volume of silicon, but we have to do this in a very controlled manner. And we need to keep a perfect control of the interface between the liquid and the solid. Yeah, so let me show you briefly how this works in reality. So first we look at the Chokaitsky method, where we have a, liquid which has been molten in a container, and then we touch the material at the surface with a seed, with solid seed, and then we pull it out, and we have this kind of rod which is solidifying, and this is the ground crystal. This is a Chokaitsky method, and the most challenging method is a float zone method. Here we have a high frequency inductor, and we are pushing from the top a rod of solid material, and it's molten. It's molten by it's being melted by the inductor, and we will see what happens next. Yeah, so this was, we can see this is a liquid part here, and it is sitting on the top of the growing crystal. Yeah, so it's a very dynamic method where the liquid is actually freely sitting on the crystal. But it's a very big liquid drop, and the diameter of this crystal is up to 200 millimeters. In this movie, it's 100 millimeters. Yeah. Okay, so that's just to give you an impression how dynamic these processes are, and of course, to make some models for such processes, we need an easy frame of reference. Let's put it that way. And the most convenient frame of reference is a case where we have a interface at a constant position. Yeah. So to be more exact, where this triple line between the liquid part and the solid part is at the same position. So if we think about all these three methods again, so this would mean that we actually have a melt where the height decreases and the crystal is moving down in this case. In this case, the crucible is moving up, so to say, and the melt volume decreases, and the crystal is increased in length. These two methods are actually continuous methods because the melt volume remains constant during the whole process because we add new material through the free surface in this case, and through the melting interface in this case. So here we would also need to consider kind of material flowing through the melt. Yeah, yeah. So this is a frame of reference which we need. And one more remark. So the triple line, it's the boundary between the solid part, the liquid part, and the gas. It's a phase change process what we have here. So this point is not freely moving. It's actually related to the melting and solidification processes. Yeah, so that's what we need to keep in mind when we make a model for this process. Yeah, so what we have done, we have tried to capture the dynamics of this process in a model, which you can see on this slide. So our starting point was Boussinesq pimple foam solver. Then we added two dynamic meshes for the fluid part here at the bottom and for the solid part. We have a common patch between both these domains, and we use motion solver to deform the geometry. And for this interface, we calculate the local motion velocity from the heat balance or the Stefan condition. And of course, we need to specify in this model, which is a local model, not a model of the whole furnace. We need to specify some local boundary conditions like radiation to the ambient or some heating profiles. Yeah, because the melt needs to be heated to remain in the molten state. So this is of course a simplified model, but it allows us to investigate these two domains, the solid and the melt, in more detail. Yes, and to consider flow in 3 dimensions and so on. Okay, yeah, so the first task is to make a new mesh, and what we tried here is to keep it at first as possible and use block mesh. Yeah, and it's quite important also for this process to have good boundary layers. Therefore, in block mesh, we have the full control of this. But if you think about these very curved geometries, well, I think you can understand that the setup becomes quite complex. So therefore, we developed a Python package where we have a possibility to connect many blocks, like up to 51 block, in a kind of object-oriented way, where the topology and the connections and grading is working automatically. Yeah, so this is what we started, and this will be published open source. So if you are interested, let me know. And here you can see a very simple example for this 2-block geometry, and this is what you actually need to write as a script in Python, and then the library generates a block mesh dictionary. Yeah, and here you can see the topology of all the geometries which I showed to you, and it goes from 8 blocks to 51 blocks. Yeah. Okay, yeah, so let me show you a few examples for all these cases. So we start with directional certification with the simplest method, and what you can see here is at the beginning we have a 10,000 seconds where we just calculate the temperatures, then we calculate also the mesh motion for more 10,000 seconds, and at the end we have 200 seconds of melt flow. Yeah, you cannot see this so well in this picture because it's showing just the temperature field, but I think you can see at least quite good the deformation here of the boundary between the solid part and the liquid part. Yes, so you can see it starts moving now. And the triple line here remains at the same position. Yeah. When we look at the flow, we can see it's what we have considered just buoyancy in this case. You can see flow pattern with quite weak velocities because the gradients are not so large in this method. But nevertheless, there are some problems here when you look at the deformation. So you need to be very careful with the mesh and mesh motion methods to keep this stable. So the second method is the Czochralski method, where we pull the crystal out of the melt, and here you can see now the crystal starts moving, and the phase interface also. And when we have the melt flow in the last 200 seconds, the whole melt gets quite mixed. And when we look at the velocities, you can see that these are quite high velocities up to 200 centimeters, up to 25 centimeters per second, and this is related to the gradients in the melt. Okay, excuse me. In this case, the triple line is quite stable. Yeah, but we need to be careful about this very intense melt motion, and actually we would also need some more accurate flow models for this, like considering also turbulence. Okay, the third method, the granulate crucible. Okay, you can see the interface will start moving now, but it remains still quite flat. And at the end, when the melt flow is starting, yeah, you can see also some mixing here in the melt. And when we take a closer look, we can again see a buoyancy flow here, but it's much weaker than in the previous case because the heating is done on the top here. In previous case, it was done here at the side. Okay, yeah. So the last example is the float zone case, where you saw the video at the beginning. So now the interface starts moving, and we can see the crystal is growing longer, and the interface also goes down, and it's also quite deformed, and this is a kind of a feature of this process. And yeah, what we can see here again for the melt, we can also have a not very strong melt convection, yeah, but it can have an important role in the process. Yeah. And here we can see a problem also with the mesh, so due to the high curvature here at the triple line. Yeah, so let me come to some conclusions. So this was the new solver, which aims to investigate the dynamics of several crystal growth processes for silicon. And in the future, we will also consider more exact boundary conditions for the temperature and also more forces in the melt. And of course, we will need to try different methods for grid deformation, yes, which are more robust. And finally, we will also need some validation experiments where we will use model experiments for this. Yeah. Okay, yeah. So the topic of model experiments is a topic of our new project, which is called NemoCris, which is financed by an ERC starting grant. And if you are interested, we are still looking for new PhDs in this project for simulations, also involving OpenFOAM. So let me know if you are interested. And thank you for your attention. I'm looking forward to your questions. Thank you.
Great. Thanks very much for a very nice talk, Kaspers, and some very nice animations. I guess we've probably time for just for one quick question. There's a few questions in the Q&A, so you may have to come back to them. Just a comment from myself: the Nemo block Python interface. I look forward to that being shared because that will be, I think, generally useful. I'll just pick the first question. So Chang Yong says, very interesting talk. Is the interface between solid and liquid treated as an internal boundary?
No, it's a boundary between two meshes, actually. Yeah? So it's not an internal boundary. So we have actually two separate meshes, and we connect these meshes by patch interpolation. Okay, is that explicitly linked, or is it like a semi-implicit or implicit? No, it's actually iterative coupling. Yeah, so we calculate these equations and the meshes after one another. Yeah, okay, so you solve one, then the other one, and you keep passing it. Yes, okay, yes, very good. Yes. Great. Let me see. Maybe time for one quick other one. Have the enthalpy porosity technique been explored, which is also available in OpenFOAM? If yes, what is the setback of using this method for the current work? Yes, there are models for silicon crystal growth also using the enthalpy method. The problem is that you for several topics, like for example, if you want to calculate the segregation exactly of various species or impurities in the melt, you need a quite exact and smooth phase boundary. So in this case, this moving mesh method has advantages, and therefore we use this method. But it's possible, of course. Then at least to have a first impression how the phase boundary would curve in reaction to the thermal field, the enthalpy method is perfectly fine. Yes. Great. Okay, there's a few more questions in the Q&A, so maybe you can answer them via the chat or via text afterwards, so we can keep going to time. So great, thanks very much again, Kaspers. Okay. Yeah, thank you. Okay, our next speaker is Mr. Hendrik Berestrand. So Hendrik, if you want to share your screen and turn on your video, feel free to start when you're ready.
Yes, hello. So screen. Can you see my screen?
Yep, I can see it perfectly and see you and hear you, so fire away.
Okay, great. So welcome to my talk. I'm a PhD student in the north of Sweden at the Luleå University of Technology. Quite a small university, but we do our stuff and we try OpenFOAM. As for this talk, just a brief introduction, talk about this model I've been working on, the grid, solver, and then some results. So in the data center CFD, my project is about quality and credibility, simulating cooling in data centers. It's about having reproducible results to then use those models to increase energy efficiency in data centers. And then to develop tools and methods to run these models in optimization sort of mindset. The goals of this work has been to model the data center facility, check the grid requirements, and compare these to solvers, which is sort of an integrity check of the OpenFOAM solvers in themselves. We know that the Boussinesq criteria has been thoroughly studied, advantages with incompressible. And we know something about the errors that we can expect. For data centers, we don't know this. So part of this has been to see the feasibility for data centers, to see how much we actually gain. And it has been demonstrated to solve the fluid flow in data centers before. So now we do it slightly more thoroughly. Data center modeling is nothing new in CFD. So here we focus a little bit on the grid sizing. Everything between 6 inches, close to 15 centimeters, to 1 inch in the open airspace region, because we know data centers are very big and we have long periods of time in between server loads and how they distribute. We have our facility in Luleå, where we have configured a cluster for OpenFOAM MPI workloads. And we do this, we use this cluster to simulate this data center test cell that we have, which can look something like this. Hence, it's a validation challenge. But here, the focus is on verification with OpenFOAM. So we have a very simplified model. It's not exactly the same data center, so we don't have to worry about porous zones and such for those cables. But it's still quite a simplification. So what you see here are 2 rows of racks, where we have cold air coming in on the blue sides. We have 10 of these racks, and then the slightly hotter air on the orange parts rising to the roof. Air comes back into the cooling units on the sides. We have 4 of them. And then cold air is delivered to the servers from these gray areas. This is a hard floor configuration. In reality, it might look something like this. We have these 2 cooling units, a porous zone in front that sends out this cold air in a uniformly distributed manner. And then we have the front side of the servers. You know, buoyant Pussinesque pimple foam and its assumption of linear buoyant, how do you say? Yeah, how density varies linearly, and the incompressible simplification. And energy equation, in this case, is very simple. And buoyant pimple foam, where we have the compressible version, we have the equation of state and an added term to the energy equation, with this pressure term off, as it makes quite a difference in convergence properties for this type of problem, for the pressure work. As for the boundary conditions, we increase rack enthalpy by the server load. And other than that, we have constant mass flow rates on everything. So it's a steady state situation, but we need to solve it transiently to estimate turbulence statistics. And there's a small opening in the roof set for the atmospheric pressure references to increase or to improve the convergence. With this sort of flows, there's no other alternative than to try to use Rounds models to get computational economy. And we have low Reynolds number enablable functions at the walls. We try 7 different grids in between 100K cells, something like that, to 2 million, even 10 million at some point, but it shows different results. And the grid is generated by Snappy Hex Mesh. Something like this for a simulation matrix to test out the Pussinesque to compressible solver. And then we try 2 different flows, a typical mass flow for server flow rates and a low mass flow for server flow rates. And as you can see for the finer grids, F to F4 here, the wall Y plus starts getting close to 30, which means we are in the finer region here. So we can't refine more because we will lose accuracy of how the Rounds models are defined. So if we then look at the solution, so here you can see a typical cross section of a solution. Low flow rates on the top for temperature and velocity magnitude. And you can see the hot aisle air coming up to the roof and then out to the servers on the sides. And then we have typical turbulent viscosities. And there's an order of magnitude lower for these turbulent viscosities when we have a lower mass flow rate to the bottom right here. solutions for the transient results on the cooling units. The air coming out can look something like this for K epsilon. And when we try different grids for Boussinesq, 7 grids here, so this is only for the Boussinesq solver, we see the returning temperatures on the cooling units. The inlet temperature, the cold temperature, is 291 Kelvin. So the degree for the outlets here is about 7 degrees difference. And for the different grids, we can see there's a difference of 0.4 degrees in between all these grids. But I've marked out the orange ones here because they are grouped up and consistent and nice those are the ones in the asymptotic regions that we can make a Richardson extrapolation of to know we have a proper solution. Being a verification study, we want to make sure we also have no numerical diffusion. So we generated this kernel density estimate to show the temperature distribution in the data center volume. These grid differences are quantified by this maximum value of the cross correlation in between these different distribution. So if we look at the graph to the left, we see the 3 finest grids. They are pretty much spot on onto each other, no artificial numerical diffusion in the volume. And that's also again confirmed on the right graph, where we see that this cross correlation starts matching up really well. And these are all in reference to the finest grid. So now we know that. We know the Y+, we know what sort of grid we need to be in that region. We can compare the Boussinesq and compressible ones by a visual inspection like this. And we see the Boussinesq one has the coarse grid, the F grid here. It's slightly off. This happens because there is recirculation into one of the servers. So hot air starts coming back and we heat it up twice. So for Boussinesq, this would have to go a slightly finer grid than the compressible one. Yes. And then if we compare the solutions for these 3 grids, we can see consistently for the pressure drop being the bottom graphs here, being in 11 Pascal range. The pressure drop is consistently higher in the compressible solver. And this has to do, I think, with the extra-terminal energy equation and also it being compressible in itself. But the trends are pretty much exactly the same, other than that, also for temperature. So that's reassuring. And we have the Reynolds numbers being high for data center typical flows. Prandtl number, essential for the turbulence of thermal diffusivity in how hot and cold air mixes in the data center. The questions can be such that we want to concentrate hot air for, how do you say, greenhouses, for instance, growing tomatoes and such. Then we want to calculate it accurately where the hot air goes and how we can load the data center to do that some types of the year. Richardson number, closely connected to the Boussinesq assumption. And we know that we have forced convection, you can neglect it when you have Richardson higher than 10. And natural convection is what we want to work towards. So we want to see, is it feasible if we take down the fan speeds to have a natural convection? So here, what we see here is comparing these typical fan speeds, giving lower temperature increase over the servers, same power usage, same boundary conditions other than that. But we lower the fan speed flow rate with 1/5. And what we see here, we have the Boussinesq result, blue, Boussinesq or compressible result in orange, and they overlap pretty much exactly for this finest grid. And then for the hot case with lower flow rates, we see that certainly there is a higher temperature generated from the servers, also acceptable in terms of CPU temperature. And they still match up pretty well, Boussinesq and compressible. Then we have just an extra point, PISO versus Pimple. I've used Pimple in all these simulations to make sure there's a consistency in time stepping. to be able to look at the grids in that way, in that regard. If we use PISO, time steps automatically become 1 to 3 milliseconds, which is rather fine. So these simulations become very time consuming, and they are. The simulations are run to sample something. It becomes something like 2 to 5 minutes to get these average values of temperature. But we see still that it's for those small time steps, there is pretty much no difference. And we come to the conclusions with that. Solvers are viable options. They're, yeah, I'm out of time, I think. Yeah. Solvers are viable options. Pressure drops are consistently high with compressible solver as expected. The compressible solver is slower, between 20–40%, though it's experienced to have better convergence. So we can rely more on that one. It possibly allows a more coarse grid. That's all from me. Thank you.
Great. Thanks very much, Henrik, for a nice talk. We have very many questions and comments in the Q&A, so we won't have time to go through them all live. So afterwards you can go through them and you can answer in the Q&A as the presenter. So I'll just we've time for just probably one question, I'd say. So let me select one of them. So Nick asks, what is the best solver in OpenFOAM that considers temperature, relative humidity, or moisture for HVAC in general?
Oh, asking me that one. Let's see. So I've thought a little bit about moisture modeling, and I found there is some guy in the community somewhere has published on his GitHub one of these ones. I think it's a German guy. So I think you try to find that one and look it up and implement it in your own.
Sure. And maybe a follow-on question then. So which should we use then? Should we use Busanesque or should we use compressible solvers? Like which ones, if they give the same answer, which one's faster and more robust?
So it depends on the boundary conditions. Turbulence modeling is what it is, right? So I'm going to continue with the compressible one here. Okay. Because I can push the mesh, so to speak, for large geometries, and I have seen that the solution time is fine. I mean, I have a cluster also, so okay. It's dependent on the situation.
Great. Okay, we don't. There's many more questions, but we don't really have time to do them live. So maybe Henrik, you can answer them during the next talk. So thanks again for a very nice talk. We're on to our final speaker for this session. So Mr. Sai Tarva from Monash. So Sai, if you want to turn on your video and you can share your screen. Great. So you can start when you're ready.
Thanks. Hi, I'm Sai Tarva. Thanks a lot for showing interest in our work. I'm a PhD student under the supervision of Dr. Daniel Duke at Monash University in Melbourne, Australia. And this work is also done in collaboration with Professor David Schmidt from University of Massachusetts Amherst, USA. I would like to first acknowledge the funding support from Australian Research Council. And today I'm going to talk about the characterization of internal flow in cavitating fuel injector nozzles. This is, I think, a blend of both multi-phase flow as well. So anyway, this project is motivated by the need for reducing emissions in internal combustion engines. So even though we are trying to cut down on emission, the internal combustion, still the mankind is heavily dependent on IC engines, and therefore we have a dire need to reduce the emissions. And as I'll show, the fuel spray atomization plays a crucial role in the emission, and the fuel spray atomization is in turn affected by cavitation in fuel injector nozzles. So let me just start by explaining what is cavitation. Basically, it's the vaporization of liquid when the flow pressure drops below the saturated vapor pressure, as seen here in the phase change diagram. And the fuel injector nozzles cavitate because the fuel rushes in from the upstream region at very high pressure and passes through a very small diameter nozzle. This is important to form a fine mist in the combustion chamber. And as the fuel passes through the small diameter nozzle, the flow accelerates, and near the nozzle inlet, the flow pressure can drop below the vapor pressure, and that gives rise to cavitation. And we all know from the marine applications that cavitation is often thought to be detrimental because the implosion of cavitation bubbles causes erosion, and that can be seen here on the injector wall, which is damaged because of cavitation. However, in fuel injector nozzles, there is an advantage to having cavitation, and that is basically researchers have seen that with the presence of cavitation, the ensuing outlet jet spray has a larger cone angle and lower sort of mean diameter. Basically, it has a better. However, the nozzle internal flow, which affects the outlet spray, is not well understood. And one of the reasons for this is the inherent limitations in the experimental investigations, owing to the scattering of light at the liquid vapor interfaces. Further, due to the small diameter and high flow velocity and pressure, numerical models are often used to supplement the experiments to characterize the flow within the. In this work, our goal is to study the fundamental fluid mechanics instead of modeling a complete prototype realistic fuel injector nozzle. Therefore, we use a canonical cylindrical geometry as shown here, which is just a change in diameter, basically, and the flow comes in and gives rise to cavitation within the nozzle. And our aim is to characterize the cavitation intensity as the function of the flow parameters. So the first step, of course, is to determine the computational models to be used. And for modeling the multi-phase flow in the nozzle, the most detailed approach is to solve conservation equations for both liquid and vapor phases. However, that is prohibitively expensive. So we introduce some simplifications. The first one is to consider a pseudo single fluid, which is kind of like a continua consisting of both vapor and liquid phases. And also we use a homogeneous flow assumption, wherein we assume that there is no momentum difference between the two phases. Using these assumptions, we can solve for the mixture density. However, we need another equation to close the continuity and momentum equations here. So we solve the transport equation for the vapor quality, which is given here by X. And on the right-hand side, we have the source term, which is the production term for the vapor. And the use of a cavitation model is to estimate the source term. For example, bubble dynamics models use Rayleigh-Placet equation to estimate the bubble growth rate. And we use homogeneous models in this work, wherein homogeneous equilibrium model uses a barotropic equation of state, which couples the pressure and mixture density. And we use a homogeneous relaxation model in this study for reasons I'll explain. So there are like two extremes in the spectrum of homogeneous models. One is the frozen model where there is no heat transfer considered between the phases. And on the other extreme lies the equilibrium model, wherein the heat transfer between the phases is considered to be instantaneous. However, both of these are actually unrealistic extremes. We would like to model something which is closer to the nature, wherein like there is a finite time taken for the heat transfer. So we use a homogeneous relaxation model, which models the non-equilibrium heat transfer using an empirical correlation. And a timescale theta is chosen to relax the fields to the equilibrium value. So this is how the homogeneous relaxation model solves for the change in quality. So it relaxes the instantaneous quality to the equilibrium quality using an empirical timescale theta. And this timescale is obtained using Downer-Zapolsky correlation, where Downer-Zapolsky had done experiments on vaporization of water in long cylindrical pipes to obtain a relationship of theta with respect to alpha, which is the vapor fraction, and psi, which is the non-dimensional pressure. Interestingly, the model parameters that they have obtained also work for the our working fluid, which is a gasoline surrogate. So moving on to the simulation setup, we are using, like I said, a canonical cylindrical nozzle, and we are to allow for computational feasibility. We are doing 2D simulations with an axisymmetric assumption, wherein we just consider a wedge angle of 1 degree, and we use a reference geometry of experiments done by Duke et al., wherein the diameter of the nozzle is 500 micron, and we are doing RAND simulations with realizable K epsilon model. And the homogeneous relaxation model code is actually in Foam Extend 3.2 environment. So yeah, this is the geometry. I'll quickly move on to the results now. Like I said, the purpose of this talk is to compare the performance of different homogeneous cavitation models. So here we compare the homogeneous equilibrium model and the homogeneous relaxation model. The homogeneous equilibrium model is actually available in OpenFOAM with the cavitating foam solver, and we compare the HRM results. So firstly, we look at the vapor fraction on the top. We see that initially cavitation is formed near the nozzle inlet and is, because of low pressure, trapped within the recirculation bubble. And then this then stretches downstream in the form of an attached cavity sheet, which is reflected in both HEM and HRM. However, as the pressure recovery occurs somewhere along the midway through the nozzle, we expect that the cavity sheet will get pinched off and shed into the downstream, and we expect a profile as seen in HRM. However, with homogeneous equilibrium model, we don't see any reattachment point within the nozzle, which is also evident from the velocity profile, wherein the recirculation bubble is much more clearly defined for HRM. And we look at the reason for this is because of the barotropic equation of state, which homogeneous equilibrium model uses, which basically couples the pressure and density tightly, and there is no baroclinic torque, which is required for the reentrant jet to form. I'll quickly show the experimental validation as well. I won't touch much upon the experimental. So experimental procedure, basically we have taken the reference experiments done by Duke et al. In Argonne National Laboratory, and where they have measured the vapor fraction in cylindrical nozzles quantitatively. This is the experiment result, and we compare that with the HRM and HEM models. As we see, and we take the radial profiles at different downstream-wise locations. We see that initially at near the nozzle inlet, both these models overpredict the cavity thickness, whereas as we move downstream, we see a better match with HRM model. And as we move further downstream, we see that the HRM model underpredicts the cavitation thickness. This is because we have modeled smooth walls, and in reality, in the experimental nozzles, we expect some surface roughness to be there, and that could give rise to extra cavitation paper to form. So with that, I conclude my talk. Basically, we see that the homogeneous relaxation model is qualitatively matching the experimental results better than the homogeneous equilibrium model. Further, if we look at the fluid mechanics involved, we see that the reattachment point and reentrant jet are also modeled better with the homogeneous relaxation model. And one more thing I would like to touch upon is that we were able to model the multi-phase flow using an axisymmetric flow assumption, which is quite problematic because multi-phase flows are inherently unstable due to a steep gradient in density, and due to axisymmetric flow assumption, we don't have the third direction to dissipate the numerical instabilities. So we had to control the boundary conditions carefully. With that, I conclude my talk. Thanks a lot. If you have any questions, I'm welcome to answer them. And these are my contact details. Thank you.
Thanks, Sai, for a very nice talk. Some nice results there. So if people have questions, feel free to put them in the Q&A. We're just over time for this session, so maybe I can just put one question to you, Sai. So from your validation, it looks like the HRM model does better, but still there's some differences with the experiments. Are there improvements to the solver or to the geometry or boundary conditions you think you plan to make to try improve the fit to the experiments?
Yeah, actually, there are a few things we are considering so that we can match with the experiment better. First is that we are using a sharp edge for the inlet corner, whereas in the experiment, I mean, no matter how good the machining techniques would be, there would still be some radius of curvature at the inlet. So we have the SEM image of the experiment nozzle, and we are thinking of looking at the actual radius of curvature and modeling that, so that that is in the expected trend. With the sharp edge, the cavity thickness is expected to be higher. So if we make the inlet corner rounded, we would see probably the a better match with the experiment.
Thanks very much, Sai. Thanks for the nice talk. And if people have other questions in the discussion, you can follow up there. So thanks again to our 4 speakers, and I'll bring this session to a close. There is a short coffee break, and then the next keynote session will start at 10 past, so in 7 minutes from now. So thanks again to everybody. We'll see you in the next session.